Hi everyone. In this video we're going to be talking about the different types of intermolecular forces, and you should be taking notes on page 2 of your packet of fun as I go through each of these. So recall that intermolecular forces are the force of attraction between molecules. Now we're going to be talking about 4 types. And the first one that we're going to be talking about is London dispersion forces. London dispersion forces are the weakest intermolecular force, and it exists between nonpolar molecules or noble gases. Now remember, nonpolar molecules doesn't create a dipole. Electrons are evenly shared throughout the whole thing, and noble gases just exist floating around. But they can be condensed, and they do have forces of attraction when they are. So again, London dispersion forces exist between nonpolar covalent compounds and noble gases. And this is the weakest intermolecular force. So if we think of a noble gas, let's do neon. I'll do it in a different color. Let's think. We have 2 neons. Say 2 neons got near each other. Now, when they do get near each other, there is a force of attraction that can occur. Now, what causes this attraction is the distribution of electrons around the neon. Now, neon has 10 electrons on it. I'm probably going to end up drawing more than 10. But those electrons are randomly moving all throughout this atom. Now, what ends up creating a very weak and quick force of attraction is when those electrons all happen to be on the same side of the atom at the same time. What it does is it temporarily creates a partially negative side, and then the other side of the atom, that positive nuclear charge is shown. What that causes is that a nearby neon, because it creates this temporary negative charge on the right-hand side of the one neon, on the other neon, those electrons are repelled to the other side of the atom. So then it gets a partially negative side on the other side of the atom, and then by default, you end up with a partial positive side. And you have this force of attraction between the neons or a nonpolar covalent molecule. Now, the reason that it is so weak is because this is considered a temporary dipole that forms. It's not natural like in a polar molecule, it's just temporary. So what I usually tell students is imagine running around a gym and your teacher's just like, you know what, I want all 30 of you to just run around this gym. Let me get a blank piece of paper. Run around this gym, and when I say stop, I want all of you guys to stop. Now, if we think about how you're going to scatter and run around the gym and you're constantly moving, when that teacher says stop, some people might be super clumped up, while other people could be all over the place. This is very similar to electrons in an atom or in a noble gas or a nonpolar covalent molecule, where those electrons are just moving around, and then by chance, they could all end up on one side of the molecule, creating a temporary dipole, and then by default, the other side becomes positive. But again, because it's temporary, this is the weakest intermolecular force that exists. The next one that we're going to talk about is a dipole-dipole intermolecular force. So it's exactly what you think. A dipole is a polar covalent compound. So this is a little bit stronger than those London dispersion forces, and it exists between polar compounds. or dipoles. Okay. Now, if we take a look, a dipole, for instance, would be like an HCl. Oops. Now, for this, here's the Lewis dot structures for HCl. Now, if we were to take a look at just one, you would see that it's not a hydrogen-carbon bond. It's not the same on all sides. It is a polar molecule. So what ends up happening is all the electrons want to go to the most electronegative side of the molecule, which is the chlorine. And so you have a natural dipole that exists, where the hydrogens are partially positive and the chlorines are partially negative. Now, because of this, when these two molecules get near each other, there ends up being a force of attraction between the partial negative side of one molecule and the partial positive side of another molecule. So because these are not temporary dipoles, because they naturally exist this way, it is definitely a stronger intermolecular force. Now, the next one we're going to talk about is actually a specific type of dipole-dipole force of attraction. So this one is still a dipole-dipole force of attraction. So this is kind of like a subcategory. And the reason that we separate it is because this dipole-dipole force is extra, extra, extra strong. The force of attraction is a lot stronger than other dipole-dipole forces. And so we have hydrogen bonding. Now, hydrogen bonding should sound familiar because you talked about it in biology last year, though you might not know the details of it. So I'm going to talk about that now. So hydrogen bonding occurs between polar compounds where there is a hydrogen that is chemically bonded to a fluorine, to an oxygen, or to a nitrogen. Now, the reason that it has to be chemically bonded to one of those three things is because they're the most electronegative elements on the table. So what that does is that when you have that hydrogen connected to a nitrogen, oxygen, or fluorine, so just remember NOF or FON, however you need to remember it, when you have a hydrogen that's connected to one of those three things, it creates a very, very, very polar bond. So you have one side of the bond, the fluorine, the oxygen, the nitrogen, that is so electronegative compared to the other side that it creates a very, very strong force of attraction when a hydrogen from a different molecule comes along and feels an attraction toward an unshared pair on one of those atoms. So we will take a look at an example of this one. So I'm going to draw out a water molecule here. Actually, I'm going to draw two because we're going to show the force of attraction between the molecules. So here we have a water molecule. The hydrogens are partially positive. Each of these unshared pairs are partially negative. By definition, hydrogen bonding is the attraction of a hydrogen that's connected to a nitrogen, oxygen, or fluorine toward an unshared pair on an atom on a different molecule. So it requires, of course, two different molecules. So here's a hydrogen again. We'll draw out that oxygen for our other water molecule. And hydrogen bonding is when the hydrogen that's connected to a nitrogen, oxygen, or fluorine is feeling an attraction toward an unshared pair on a different molecule. So here we have a hydrogen bonding force of attraction that occurs because here there's the hydrogen bonded to an oxygen, which we can check off our little box here, and there's an unshared pair on another molecule. Okay. This is the hydrogen bonding is the strongest dipole-dipole force of attraction. Okay. The very last one that we're going to talk about is ion-dipole force. So it's exactly what you think. It's going to be an ion from an ionic compound feeling an attractive force toward a dipole from a polar covalent compound. Now, unlike our previous example where we were looking at two water molecules or two neons, this one requires two different molecules, or sorry, two different compounds in order to get this force of attraction. So it is between a polar covalent molecule and an ion from an ionic compound. And this is the strongest intermolecular force out there. So if we take a look, we can think about how water dissolves a salt. Okay, so an instance of that would be like NaCl. Na is a metal, chlorine is a nonmetal, so that's an ionic compound. Now when you put salt into water, that salt disappears. But the thing is that the NAs and the Cls are still there. They've just been separated from one another. And those water molecules did it through this ion-dipole force of attraction that the water has toward the chlorine or the sodium. So in this ionic compound, the sodium is positive, the chlorine is negative. Each of these are ions. Now when you introduce it to water, you have a dipole. Okay, where your hydrogens are partially positive and your oxygen sides are partially negative. Okay, so everything wants to go that way. Now when you introduce an ion to it, you end up getting a force of attraction between the positive hydrogens and the negative ions. And then another water molecule can come around. So here, I'll draw it like this. And you end up having a force of attraction between this partial negative oxygen and the positive ion, and it separates those ions. So to draw this a little bit more clearly, or simply, and you can see it in your packet of fun, your ion-dipole requires a positive ion that's a full positive charge, so it's fully lost an electron, and it forms between the partial negative side of a dipole. Or you can have a negative ion, which has a total negative charge, or -2 or -3 charge. It feels an attraction toward the partial positive end of a dipole.